Topic 6.1, or sorry, topic 6 alone is called kinetics. So if you think of kinetic energy, we are bringing that concept, that's a physics concept of energy, and bringing it and looking specifically what the motion of atoms and the energy of atoms that allow for kinetic energy to move forward. And so 6.1 is looking at what are the rates of reactions and how to affect them, how to measure them, so on and so forth. 6.1 is going to be done in 2 videos, just to break up the length of all of 6.1 because it is the only SL topic or subtopic in topic 6. So what is the rate of a reaction? The definition is quite literally looking at the rate of change based off the concentration. So let's look at the units, right? So here, moles per decimeter cubed is the unit for concentration. And second to the -1 is the unit for rate. Therefore, moles per decimeter cubed per second is the unit for rate of change. And we know this because rate is measured in time. Whenever you're looking at something, you're looking at a change over time. Therefore, the unit we're looking at, concentration, the change in concentration over time, and the MKS is, of course, seconds, hence S, and IB does the inverse, so second to the -1. Therefore, when we're looking at the rate of reaction, we are quite literally looking at how quickly a reaction happens. So we want to look and compare the ratio of the concentration of reactants to the concentration of products. Therefore, we would expect as the reaction moves forward, the concentration of reactants is going to decrease, and the concentration of products is going to increase. So if we're looking at rate of how quickly this is going to occur, our rate of reaction, which I will shorthand ROR, is going to look at the decrease in the concentration of my reactants over time, right? So ideally, what we are looking at is the change in the concentration of my reactant over the change in time or the course of the reaction. And then, of course, vice versa, we expect to have an increase in the concentration of products over that same course in time. Therefore, we are looking at the change in the concentration of my products over the change in the time and the course in which it's happening. Now, just for visualization purposes, when we're looking at the change of reactants, we put a negative number in there, and it's not that the rate is negative, but that's just showing that you have a decrease in concentration, not that the rate is negative, because rate can't go negative. Rate is always a positive value. It's just essentially showing you which direction are we increasing concentration or decreasing concentration at that time. If we were going to look at this in a graphical form, because they like to use graphs with these, right? So we have our graph, right? So we have time. And then over here on the y-axis, we have the concentration. So if we have a concentration of reactant, okay, we expect a lot of reactant to begin. And over time, we expect that to decrease, right? And then vice versa, if we're going to look at the concentration of our products, I'm just going to put a different color. We would expect our products to start really low, right? Essentially 0 products, and we would expect it to increase to the point where if we had a full transition, the amount of products we make should equal the amount of reactants we used. My blue line didn't go all the way down to the 0. It probably should have, but that is essentially what we're looking at when we look at a graphical representation. So different forms of graphical representations in looking at and how to read a graph when looking into determining rate. So if we have here, we have 2 reactions. We have A and we have B, right? So if we're looking at the 2 rates, how do we determine which rate is going faster? Well, you want to look at the steepness of the gradient, right? And the gradient, as you guys know, is the slope. And that is going to give you a measure of your rate. However, if you notice, there is a curve and there will always be a curve to rate graphs because of how fast a reaction is going to move forward, and then as you decrease the concentration of reactants, the reaction takes longer to happen. And we'll talk about why that occurs a little later. But due to that curve, we can only measure rate at one point in time. All right, so if we look at the steepness and we have A versus B, we see that A has a steeper curve, and therefore it's going to have a higher rate because it had more loss of concentration in the same amount of time being measured. So how do we measure that rate at one point in time? Well, this is called taking a tangent or taking a tangent graph. And so just to kind of give you an idea, if you're given instructions to draw a graph, drawing means you're going to create a scale and plot actual points on a graph. If it says sketch a graph, you're just looking at a trend. So the graph I just showed you was a sketch. This one that you see right now, that is if you are having to draw a graph. And you'll have an example in your homework of where you actually have to draw a graph. And of course, in class you can use Excel, but on the test, they would expect you to take the time to make the graph. So when we're looking at a tangent, and we're looking at a tangent of the graph, we want to take the tangent at one point in time in order to measure the rate. So you can see that they wanted to look at the tangent at 120 seconds. All right? And we're going to do that. So we go up, and you can see the dotted line. They're going to take this point at 120 seconds and find that point on the graph. And you might be like, well, how do you know how to take that tangent, right? There's so many different ways in the angle the protractor can go. And so how do you know it is the right point? Give you a clue. You'll get a more accurate value for the slope of the tangent if you draw it as long as you reasonably can so that the y value, or your concentration, and the x value, or your time, are as large as possible. So you want to position your protractor or piece of paper, whatever you have to use, to make sure you have the highest y and highest x value possible, and that will give you the most accurate data. And so looking at that point in time and looking at the example, okay, we have our concentration, 2.40. If you notice there's a negative there, right? Well, that negative is just telling us that we have a decrease in concentration. And then we have our time on the bottom, 2.83. And so these numbers, where we get these, are from where the tangent crosses your axes. Okay? And so that's where those numbers are going to come from. And then that is going to give you your value. So here we have negative 8.48 times 10 to the negative 3 moles per decimeter cubed per second, because we're taking concentration and divide it by time. And again, it's a negative number because we are seeing a decrease in the graph, which means we are looking at the concentration of your reactants. Usually they're going to tell you, or no, not usually, they will always tell you in the question where to take the tangent. And so depending on what it's asking, they'll say take the tangent at 60 seconds, take the tangent at 240 seconds, or whatever. But let's say they say take the initial rate. The initial rate is at time 0, all right? So time 0 is going to be your initial rate. Keep that in mind, because that is when the reaction initially occurs. And then by taking at time 0, as you can see over here, you are able to look at the initial rates of reactions for different reactions under different conditions or different concentrations or whatever it happens to be, and now we can have a comparison point. And also, if you look, the curve shows that the rate is not constant as you go through, and we talked about this just previously. It's greatest at the start, and it slows with progression because you're decreasing the amount of reactants present. Here's just another example that I just want to make sure you could see. Looking at the one in red, right? So here we're taking the tangent at 0 seconds. So this is going to give you your initial rate. Again, the value has a negative number, which means we are looking at the concentration of your reactants. Also, we're looking at 90 seconds, right? So we're looking at 90 seconds, and again, they're making that tangent so you have the largest y and largest x values. And again, looking at your initial rate, they're taking the largest value possible without connecting any part of that tangent to the rest of this graph. So just again, wanting to show you what the picture looks like at different tangents. The rest of this video is going to be dedicated to looking at techniques for measuring rates of reactions. There are 6 of them. First, change in volume if a gas is being produced. So how you know this is a good method to use is if you produce a gas. Just letting you know. You can use either a gas syringe or you can use the water displacement method. All right. We do not personally at Rampart High School have a gas syringe. That is an expensive setup. They're extremely expensive, therefore we don't use it. We are going to be using the water displacement. So what you do is you're going to have your bucket full of water and you're going to have an inverted eudiometer. Okay, and so we don't use a burette. We actually have eudiometers which close off right here, and it looks like a really big test tube, but it is as small of increments as a burette. And then you're going to have a reaction going on in a test tube, in a flask, whatever thing you can, and it's going to be closed off with a cork so you don't let any gas escape. And then you're going to have a tube going from the reaction to your inverted eudiometer. And eventually, as the gas is going to bubble up, you are going to see a decrease in that gas or that liquid. That liquid's going to be pushed out, and you're going to see how much gas is being produced. Now, the limitations to this method that we are looking at is depending on the gas, especially like CO2, the gases can be soluble in water depending on the temperature of the water. So you have to be very careful on what kind of gas you're producing in the reaction to know if you're able to use the inverted eudiometer. And because we're looking at rate, correct, we want to make sure we are collecting data at intervals so that we have that seconds. And that's going to produce for us a rate graph. Okay? So here is an example of a rate graph. We have our time, and we've got our volume of gas production, right? And depending on how much time we have going on there, we are going to see what that slope looks like. So an example of a reaction that this could occur with would be magnesium. So we have solid magnesium ribbon, and we put it into hydrochloric acid, right? And looking at this reaction, it's a single replacement. We'll get magnesium chloride, and that's going to stay aqueous. And here we get that hydrogen gas production. And because hydrogen gas is such a lightweight gas, the best way to capture it and to measure how much is being produced would be looking at the water displacement method. Then we can look at change in mass. This is going to be good if you have a heavy gas that's being produced in a reaction. So if you're producing hydrogen gas, not a good method. But if you're producing a heavier gas like CO2, this can be done because CO2 is soluble in water at cooler temperatures. So you're not going to potentially get as much CO2 production in actual gas form, depending on the temperature of your water and your inverted burette. So you have to be careful with this. You're going to use a balance with a reaction in the flask on top. And then we personally do not have balances that hook up to our Logger Pro. So you would quite literally have to take the measurements every 5 seconds with your eyeballs That's really old school technology, and that is what you would have to use, but you could still do it, and then you could graph it through Excel. Again, you're going to want to collect data at intervals so that you can produce a rate graph. And that way you can look at the mass being lost over time, because you're going to be losing something. So we expect a decrease in the graph because we're looking at a loss. In the previous one, we expected gain because we're looking at how much of a product we're producing. So a good example of a reaction is if we have calcium carbonate, and it's going to be a solid plus aqueous hydrochloric acid. You're going to produce calcium chloride, CO2, which is a gas, and water. Well, we know the aqueous and the water solution, right? Those guys, they're not going to leave the flask, so they're not going to change mass because we know the law of conservation of mass. But as long as you have an open container, the gas can escape. And so your gas can escape, and it's a heavy gas. We know that from its molar mass. And since it's a heavy gas, you would see a change on the scale due to the loss of CO2. And based on your ratio, your mole ratio, you could have predicted how much you lost and what should have been produced. Third, looking at the change in transmission of light, which is really cool. Actually, it's a really neat piece of technology. You could look at colorimetry or spectrophotometry. So it is good if one of the reactants or products are colored, and so you either see a loss of color or a gain of color. And or you could look at a clear solution going to a cloudy solution or a cloudy solution going to a clear solution. Either one of those works. But this is going to give you a characteristic absorption in the visible range. So if you know what it is you're working with, you can pass a specific wavelength of light through a solution, and then that can be measured based off the probe that you're going to use. Now, I've always done transmission of light, not actual color itself. And so as the solution gets more and more cloudy due to a precipitate formation, you have less and less light getting through and being dissipated. And so you look at what the change of overall transmission of light. They both work. So one's called colorimetry, so looking at color, and one's spectrophotometry, looking at how much light gets passed through. So this is what happens, is you have a light source. And so we have a machine, it's called a spectrophotometer, and it's going to pass a light through a cuvette. A cuvette is a really tiny piece of plasticware. In that cuvette, you're going to have a solution, right? And that solution is going to react. Well, as that light's being passed through, it's going to separate out either the different colors, or it's going to allow less light to go through. And then it's going to hit this diffraction grating like a prism, and you will see a spectrum, and you may see missing lines because it's an absorption spectrum, and then you could determine what kind of reaction has occurred. Again, you're going to collect data at intervals and create a rate graph. And this is really cool. So this is what we actually have a Logger Pro for this. I've never personally used it, but we do have a Logger Pro. And so this is the data that would be produced. So we have our graph, and the rate graph is right down here, right? And so you can see what it looks like, the absorption at a specific wavelength over time, and you can see that it's decreasing. And so you can also see from the graph that we are looking at this wavelength in particular. And so our absorptions is happening at 591.0 nanometers. And so whatever color or whatever reactant is giving that band off, we're seeing a decrease in it over time, so on and so forth. Fourth, you can have a change in the concentration measured by titration. So a titration is a method where you are going to titrate a reaction by a known standard. And there's lots of different titrations you can do, but usually it's going to be working with acids and bases and creating a neutral solution. The problem with titrations is they cannot be done continuously as the reaction proceeds, because the reaction is still going to go on either in your burette or it's going to occur in the flask, whatever it is you are measuring and where you're measuring it. So you can't get really good what is the initial, what's 20 seconds, 30 seconds, so on and so forth. So what we have to do is you're going to take samples of your reaction. So you're going to have your reaction going on in your glassware, right? So reaction going on. And you're going to start it. So you're going to start your timer. And let's say at 20 seconds, you're going to take some of that reactant and you're going to take it out. And then you're going to quench it. Quenching is a stopping agent so that your reaction does not move forward. And this is going to give you a snapshot of what happened after 20 seconds, after 40 seconds, after 5 minutes, whatever it is. And you're going to constantly repeat until you think the reaction is going to be done. So where we've used this, or an example of reaction, I should say, of what we have used this for, is if we have H2O2, so hydrogen peroxide, and we're going to react it with acidified potassium iodide. And so specifically we want to look at the H plus ions of the acid and the iodine ions of the potassium iodide. And as this reaction proceeds, you see the formation of iodine. And so there's actually a color change that occurs, and water. So what we're going to do is we are going to, at different time intervals, we are going to pull out part or a little bit of this reaction, and we're going to quench it. And we're going to quench it with sodium carbonate. And then we are going to titrate this quenching. So this is what gets titrated, is a solution that's been quenched. And we are going to then titrate it against a known standard. And that's going to differ based on the reaction we're working with. And so here we have our titrant Na2S2O3, and we're going to titrate whatever it is we quenched here, which is going to be the concentration of our products here, to see how much of the titrant we use. And then based off a mole ratio, we can figure out how much is present of both our reactants and products at that time. The fifth one is looking at the change in concentration measured by conductivity. So with conductivity, we're looking at total electrical conductivity, which is the total concentration of ions and charges that are occurring in the solution. We can use a conductivity probe, which we have, and so you can hook that up to a Logger Pro and see the change in conductivity over time. But what that conductivity probe is looking at is either an increase or a decrease in the ion concentration as you move through a reaction. And based on an increase or a decrease, conductivity response. Now we haven't talked about conductivity yet, but conductivity, you have to have ions in the solution in order to close the circuit. So as you have a circuit going on in a solution, and we have our probes in there, right? Your positive and your negative ions are going to move to their appropriate sides, and that's going to close the circuit to create a charge. And we're going to read that off a voltmeter. So an example reaction, and this is more of a topic 9 type of method, but it still allows us to look at rates of reactions that occur with conductivity. So if you look at our reaction here, right, we have ions present on the reactant side and no ions present on the product side. And so we would expect to see a decrease in the ion concentration. Therefore, we see a decrease in conductivity. Lastly, we have the non-continuous methods, and these are called clock reactions because we're using a clock to figure out where we're pulling information from a reaction. So you're going to make an arbitrary endpoint to a reaction if you know what the reaction looks like. And so you're saying, I'm going to run this reaction for 1 minute, and however much is produced in that 1 minute, I'm going to collect that data. You may not have equipment for that particular reaction, or you don't have a titrant, you don't have a quenching, you don't have a conductivity probe, something. There's a reason, and so we use these non-continuous methods. But what that allows us to do is we can change something in a reaction and run different reactions under different conditions, and then you stop the clock at the same time. And so then you can look at what is the concentration, what is the change in volume, whatever it happens to be. The only difference is you're not able to graph a rate graph, because you're not taking one reaction and looking at the change over time. You're looking at just how fast did that reaction move forward to that end point in time, and doing that for multiple different reactions. And therefore, you get an average rate over time, which is never going to be better than taking an actual rate graph, but you can do that if we don't have the supplies that are needed to run one of the other reactions. So you could do this using different masses of magnesium ribbon in a dilute solution of hydrochloric acid, and however long it takes for all the ribbon to disappear, or at 1 minute, how much ribbon is left behind, and then mass that ribbon. There's different ways in which you can do that.